So, myself Punniyamurthy from IIT Guwahati. I welcome you all to IIT PAL program. In this class, we will study about carboxylic acids. Carboxylic acids are organic compounds that contain COOH functional group. So, they can be aliphatic and aromatic. Examples: if you look at it, the carboxyl carbon, right, we can write like this. So, the carboxyl carbon is bonded with alkyl group, for example, methyl group is an example for aliphatic. In this case, is bonded with aryl group, therefore, is called aromatic carboxylic acid. Large number of carboxylic acids are abundant in nature, and carboxylic acids that contain C12 to C18 carbon atoms are called fatty acids. These are long chain carboxylic acids, and they are obtained by hydrolysis of animal fats and oils. Therefore, they are called fatty acids. Carboxylic acids also serve as precursor to make acid anhydrides, acid chloride, amide, and esters. Now, let us look at the nomenclature of carboxylic acids. In common system, the carboxylic acid names are derived from Latin or Greek words. That indicates the source of carboxylic acid. For example, formic acid. This is the first of this series of carboxylic acids, and this Latin is formica, that means and so next is acetic acid. In Latin, astem, that means vinegar. In simple carboxylic acid, better known by common names, the names are derived from Greek or Latin words that indicate the source, natural source of the carboxylic acid. These are the two examples, you can go like that, and they do not have any general rule, but however, if you look at it, first one is formic acid, then acetic acid. If you look at it, formic, I see all common names and end with IC acid, acetic acid, formic acid, propionic acid, IC acid, and butyric acid. So, if you look at all the names ends with IC and acid, formic acid, acetic acid, propionic acid and butyric acid. These are examples for monocarboxylic acids. There are also dicarboxylic acid, for example, this is known as oxalic acid. Malonic acid. Look at it at the end with IC acid, and these are examples for aliphatic dicarboxylic acids. For aromatic carboxylic acids, this is known as benzoic acid. This is known as phenyl acetic acid. This dicarboxylic acid is known as phthalic acid. So, these are the examples for aromatic carboxylic acid. These are the common names, and if you look at all the acids, as I mentioned earlier, she ends with IC acid. So, now let us look at the IUPAC system. In IUPAC system, carboxylic acids are called alkanoic acid, and for example, just we have seen. So, a common name of this is formic acid. This just we have seen name of this carboxylic acid as formic acid, common name. The IUPAC name is methanoic acid. The corresponding alkane is methane. The E has been replaced by OIC acid. So, this is called alkanoic acid, and this is the name of the alkane is methane, and E has been replaced by suffix OIC and ACD. This is called methanoic acid, and similarly this is known as ethanoic acid. Ethanoic acid. The corresponding alkane is ethane. You can see here the E has been replaced by OIC acid and propionic acid. Basically, in IUPAC system, the names of carboxylic acids have been derived from the corresponding alkanes by replacing the suffix E with OIC acid. And these all are examples for aliphatic carboxylic acids. Now, let us see few examples for dicarboxylic acid. Just we have seen name of this dicarboxylic acid as oxalic acid, and the common system IUPAC name of this is ethane dioic acid. You can see here ethane is there, and I have added di and oic acid, and similarly this one so this is known as propane dioic acid. These are the examples for aliphatic dicarboxylic acids. So, now let us look at examples for aromatic carboxylic acids. This is in IUPAC system is known as benzene carboxylic acids. Benzoic acid also is used in IUPAC system. So, both can be used for this carboxylic acid, and the next example is this IUPAC name of this carboxylic acid is 2-phenyl ethanoic acid. Just we have seen, and if you have CH3 ethanoic acid, and second carbon is now substituted with phenyl group, therefore 2-phenyl ethanoic acid. And IUPAC name of this dicarboxylic acid is benzene 1,2 dicarboxylic acid. Just we have seen a few examples for aliphatic and aromatic carboxylic acids, and if you look at in IUPAC system, their names are derived from the corresponding alkanes by replacing the E suffix E with OIC acid, and all the cases you can see here. And this all are simple carboxylic acids. Let us look at now one longer chain carboxylic acid. We have to find out the longest chain that contain the carboxylic acid functional group. This is the longest chain, and once we find it out, we have to start numbering from the carboxylic acid. So, then we have to combine the name and position of the substituent with the name of the carboxylic acid. In this case, we have a substitution at 4 and 5 carbon atoms. Therefore, 4, 5 dimethyl heptanoic acid. The IUPAC name of this carboxylic acid is there, and so 4, 5 dimethyl heptanoic acid. We can name like this any carboxylic acid we can name by numbering and placing the position as well as substitution name before the as prefix to the carboxylic acid, and this is the how the name for long chain carboxylic acid. Just we have seen the nomenclature of carboxylic acids. Now, let us look at the structure of carboxylic acid. The carboxyl carbon exhibit lower electrophilicity comparing to the carbonyl carbon. This is because of the following possible resonance structures. So, because of the possibility of the following resonance structures, a carboxyl carbon is less electrophilic in nature compared to the carbonyl carbon. Now, let us look at the preparation of carboxylic acids. The first example is oxidation of alcohol to carboxylic acid. Alcohols can be readily oxidized to carboxylic acid via aldehyde using KMnO4 in neutral, acidic or basic medium. We can also use potassium dichromate K2Cr2O7 or chromium trioxide. So, these usually carried out in acidic medium. So, you can also use potassium dichromate, chromium trioxide in acidic medium that can also oxidize alcohol to aldehyde, then further oxidation to carboxylic acid. Now, let us see one example. For example, if you take propanol and when you treat with chromium trioxide CrO3 in acidic medium, it can oxidize to aldehyde. So, this can be further oxidized to carboxylic acid. So, this is known as Jones reagent. So, when you dissolve chromium trioxide in sulfuric acid and dilute condition, this called chromium this Jones reagent. This is widely used for the oxidation of alcohol to carboxylic acids, and so this reaction usually carried out in acetone as solvent. Let us see the mechanism of this reaction. Can undergo 1 to addition here to this intermediate. Once you form this intermediate, water can remove this hydrogen form this intermediate. This so this OH minus you produce from this can react with hydronium ion to produce water molecule. Now, this is called chromate ester. So, this water molecule can act as a base. This can remove this hydrogen that can lead to the formation of the aldehyde. You form this aldehyde plus you form this chromium species. This can now this can react this is known as chromate ester, that now this water molecule can react, remove this hydrogen and you form aldehyde plus this chromium species hydronium ion. This can transform into chromium 4 species. So, if you look at it, this is a chromium 6. This chromic acid reacts with the alcohol and you generate the ester. That ester transform into aldehyde and where you generate the chromium 4 species. It is a 2 electron oxidation process. The chromium 6 is reduced to chromium 4 and your alcohol is oxidized to aldehyde. Once you form the aldehyde again can react. Since the reaction is performed in acidic medium, it can react with the presence of acid with water can form astal. That astal again can react with this chromic acid. It can go on like this, then you will end up with the carboxylic acid. How the oxidation reaction takes place? The next reaction is oxidation of alkyl benzene. For example, methyl benzene or ethyl benzene can be oxidized to benzoic acid irrespective of the substituent, whether methyl group, ethyl group, they can be oxidized. The side chain can be oxidized to benzoic acid, and this reaction can be carried out using KMnO4 in the presence of potassium hydroxide. First, it is converted into the carboxylate when you do the workup, get benzoic acid. So far we have seen two oxidation reactions. One is the oxidation of alcohol to carboxylic acid via aldehyde, first converted to aldehyde, that aldehyde undergoes further oxidation to carboxylic acid. Next we have seen the oxidation of alkyl benzene to benzoic acid. This is very important reaction, and the alkyl chain, whether it is methyl, ethyl or other alkyl group, they can be oxidized to the corresponding carboxylic acid, benzoic acid. The next example is reaction from alkyl halide. For example, if you have, so this alkyl bromide, this alkyl bromide can react with sodium cyanide to give the corresponding nitrile plus sodium bromide. This is a nucleophilic substitution reaction. Once you form the nitrile can be transformed to the corresponding amide by hydrolysis. When you react with it can be transformed to the corresponding amide that can further undergo reaction to give carboxylic acid. So, this if you have alkyl halide, the alkyl halide can be transformed to the corresponding carboxylic acid. What we do here, we add one carbon extra. Here, if you look at it, we add one carbon extra that comes from the cyanide. The other example is, this is the one of the reaction how you can transform alkyl halide to the carboxylic acid, and the other example is you can also react the alkyl halide with the magnesium So, the magnesium insertion takes place to get this is known as Grignard reagent, and magnesium 0, the insertion takes place, you get the magnesium bromide, alkyl magnesium bromide. And once you form this one, you can react with the carbon dioxide, and this reaction is usually carried out in dry condition in diethyl ether or THF. Then the addition takes place to give this intermediate. Once you form this one, this can be converted into carboxylic acid. If you look at it, we have started with alkyl halide having 3 carbon atoms, we can end up with carboxylic acid having 4 carbon atoms. We have we add one more carbon from the carbon dioxide. This is also very useful reaction. So, we have seen 2 examples under oxidation how you can convert alcohol to carboxylic acid via aldehyde. Then we have seen the oxidation of alkyl benzene to benzoic acid. Then we have seen 2 examples and reaction with alkyl halides, and where you can convert the corresponding nitrile by nucleophilic substitution. That nitrile can be transformed to the corresponding carboxylic acid via hydrolysis. And furthermore, if you have alkyl halide that can be reacted with magnesium to form Grignard reagent, that Grignard reagent can be reacted with the carbon dioxide, and that can give the corresponding carboxylic acid with 1 carbon more. The next example is you have acid halide, for example, so when you treat this acid halide with water, it can transform into carboxylic acid. And similarly, if you have anhydride, this also can undergo reaction with water to give 2 molecule of carboxylic acid. The other method that we use commonly in the laboratory is hydrolysis of esters. For example, if you have this ester, and when you treat this ester with acid or base, it can undergo hydrolysis to give So, similarly, when you can also react with the base, you will get carboxylic acid. Let us see the reaction pathway, how the reaction takes place. So, ester undergoes protonation to give this intermediate. So, this is a reversible reaction. Once you form this one, it can react with water to give this tetrahedral intermediate. Once you form this one, this can transform to this intermediate and protonation can give this, and once you form this one, so you form methanol and the carboxylic acid. This is an example for how the hydrolysis of ester takes place to give carboxylic acid and alcohol in the presence of acid. So far we have seen the preparation of carboxylic acid. First we have seen the oxidation of alcohol to carboxylic acid, then we have seen the oxidation of alkyl benzene to benzoic acid. Following that, we can see we saw how you can convert alkyl halide into carboxylic acids. Two types of reactions we have seen. The first one is alkyl halide to the corresponding nitrile by nucleophilic substitution, followed by hydrolysis to carboxylic acid. And another example we have seen, we can convert into Grignard reagent that can be reacted with the carbon dioxide to give the corresponding carboxylic acid. And these two examples, we can have one carbon extra, and then we have seen the hydrolysis of acid chloride, acid anhydride to the corresponding carboxylic acid. At the end, we have seen hydrolysis of ester to carboxylic acid. We have seen the mechanism. The reaction takes place through tetrahedral intermediate. Physical properties. Carboxylic acids that contain up to C9 carbon atoms are liquids at room temperature and exhibit strong odor. So, carboxylic acid that contain up to C9 carbon atoms, aliphatic carboxylic acids, that those are liquids at room temperature, they exhibit strong odor. Carboxylic acids that contain more than 10 carbon atoms are generally solids at room temperature, and they are generally odorless. Carboxylic acid that contain more than 10 carbon atoms are wax like solids at room temperature, they are generally odorless. Regarding the boiling point, when you increase the molecular weight of carboxylic acid, the boiling point increases. And if you compare the boiling point of carboxylic acids with aldehydes, ketone and alcohols, carboxylic acids show higher boiling point comparing to aldehydes, ketones, alcohols. This is because of the association of carboxylic acids via intermolecular hydrogen bonding. For example, if you take consider acetic acid or ethanoic acid, its molecular weight is 60. The boiling point is 118 degree. And if you compare with its corresponding alcohol that has a similar molecular weight is propanol. The boiling point is 87. So, this is because of the association of carboxylic acid via intermolecular hydrogen bonding. For example, acetic acid exists as a dimer even in wafer phase or in aprotic solvent. So, because of this hydrogen bonding and carboxylic acid show higher boiling point in comparison to aldehydes, ketones, alcohols. For example, in this case, and both these compounds carboxylic acid, alcohols have same molecular weight. However, the boiling point of carboxylic acid higher than alcohols. This because of intermolecular hydrogen bonding between the carboxylic acids. With respect to solubility of carboxylic acids, the first 4 member of this series, formic acid or methanoic acid, acetic acid, propanoic acid, and butanoic acid, they are soluble in water. The first 4 members of this series, methanoic acid, ethanoic acid, propanoic acid, butanoic acid, they are soluble in water. This is because of hydrogen bonding with water. So, these carboxylic acids as you can see here, these carboxylic acids make hydrogen bond with water and they are soluble in water. However, when you increase the size of this alkyl group, when you go for C5 or C7, 8, 9, 10, they are more hydrophobic in nature, they are insoluble in water. And this about the aliphatic carboxylic acids. When you talk about aromatic carboxylic acid, they are whether benzoic acid or naphthoic acid, they are insoluble in water. Okay, in summary, today in this class we have seen the structure, nomenclature, preparation and physical properties of carboxylic acids, and with this we will conclude this lecture, and the part 2 we will study about the chemical reactions of carboxylic acids. Thank you.